Suppose that you're building a shopping website and you want to let customers sort items by price. Should your website use selection sort or merge sort? Both algorithms will correctly sort the codes, so maybe you would just toss a coin to decide. But if there are many codes, sorting may take a long time, and our customers are not going to wait hours just to see some code prices. Thus, we should choose the algorithm that takes less time to complete. But is one sorting algorithm significantly faster than the other? To answer this question, we need to first decide how to measure performance. We would like to compare the sorting times, but sorting times depend heavily on the available resources. Instead, we can estimate the sorting time by counting the number of pop and push operations performed during the sort. We can reasonably assume that the sorting time is proportional to the number of stack operations needed to complete the sort. The following is a table that shows the number of push operations performed for collections of 4 different sizes. For example, a stack with 8 elements requires 60 push operations using merge sort and 72 push operations using selection sort. Here's an animated comparison of selection sort and merge sort for 16 elements. As the number of elements increase, both merge sort and selection sort require more operations. But notice that the number of operations increases much faster for selection sort than merge sort. For example, when there are 4 elements, the same number of operations are needed for both sorts. But for 32 elements, selection sort requires more than 2 times the number of operations as merge sort. In other words, selection sort takes more time to complete than merge sort. Why is that? To understand the performance discrepancy, let's break down the sorting algorithms into smaller parts and calculate the number of operations required by each part. As we will see, there is a relationship between the number of operations and the number of elements in the stack. Thus, we can express the performance of the algorithm in terms of the stack length. For the analysis that follows, assume that the stack contains n elements. Let's begin with selection sort. Here is a rough outline of the algorithm. First, find the maximum element and move it to the sorted stack. Then repeat step 1 until the stack is empty. Step 1 requires n pop and n push operations to find the maximum, 1 pop and 1 push operation to move the maximum value to the sorted stack, and n-1 pop and n-1 push operations to move the other elements back to the original stack. Let's just count the push operations and multiply by 2 later. Then step 1 requires a total of n times 2 operations. This is an approximation, as the exact number can slightly vary depending on the implementation. In the second iteration, the stack contains n-1 elements. Thus, n-1 times 2 operations are needed, and so forth. There are n elements, and we remove 1 element per iteration, so step 1 is repeated n times. The following table illustrates this process. The total number of operations is approximately n times 2 plus n-1 times 2 plus n-2 times 2, and so on, plus 1. Or n plus n-1 plus n-2, and so on, plus 1, multiplied by 2 minus 1. Using the summation formula, this reduces to n times n plus 1 divided by 2 times 2 minus 1. We are mainly concerned with orders of magnitude, so we can remove constants and constant factors such as 2 and 1. then the total reduces to n times n, or n squared. We can describe the performance more formally using the big O notation. We simply call the O function using our total as input. In other words, the performance of selection sort is O of n squared operations. Intuitively, each step requires an average of around n divided by 2 operations, and there are n steps, so the total number of operations is around n times n divided by 2. Now let's analyze merge sort. Merge sort consists of two basic operations. Step 1, split the elements, and step 2, merge the elements. To split n elements, we move the top half, or n divided by 2 elements, to a new stack. To merge two stacks, each with n divided by 2 elements, we compare and move a total of n elements to a new stack. We also need to reverse the merged stack, which requires another n moves. In total, each iteration takes around 5 divided by 2 times n operations. Now, how many times do we need to perform the split and merge operations? Let's begin with the split operation. Recall that we split the stack until the stack length is 1. Starting with n elements, after the first split, we have two stacks of n divided by 2 elements. After the second split operation, we have two groups of n divided by 4 elements. Later, we will also split the other half into two groups of n divided by 4 elements. So in total, we create 4 groups of n divided by 4 elements. After another round of split operations, we create 8 groups of n divided by 8 elements, and so on. How many times can we split the stack before we have 1 element per stack? This question is somewhat tricky, but it becomes easier when we work backwards from 1 element. That is, how many times do we need to double 1 to reach n? Starting from 1, if we double once, then we have 2 elements. If we double twice, we have 4 elements per group. If we double x times, then we have 2 to the x elements per group. We stop when there are n elements per group. In other words, we stop when 2 to the x equals n. Then x is equal to log of n. The log function above is base 2. Thus, starting with 1 element, if we double log n times, we end up with n elements. Similarly, starting with n elements, if we half log of n times, we have n groups of 1 elements. The following table shows how a stack of 16 elements are reduced to 16 stacks. After 1 split, there are 2 groups of 8. After 2 splits, there's 4 groups of 4. After 3, there are 8 groups of 2 elements per group. And after 4 splits, there are 16 groups each with 1 element. For n elements, the table would contain log n rows. Next, let's calculate the number of operations at every row of the table above. We split 1 time to create 2 groups of 8 elements. This requires 8 push operations. Then we split each half to create 4 groups of 4 elements. We split twice, and each split requires 4 push operations, so the total is 8. Then we split each half again to create 8 groups of 2 elements. We split 4 times, and each split requires 2 push operations, so the total is 8 again. We split each half again to create 16 groups of 1 elements. We split 8 times, and each split requires 1 push operation, so the total is 8. Each row requires 8 operations, and the table has 4 rows, so the total is 32 operations. For a stack of n elements, Each row requires n divided by 2 operations, and the table would contain log n rows. So the total number of split operations is n divided by 2 times log n. Let's now consider the merge operations. Any stack we split will eventually be merged, so the number of merge operations is equal to the number of split operations. Since a merge requires 4 times as many operations as a split, the total number of operations is equal to n divided by 2 times log n plus 2 times n times log of n for the merges. Then the total number of operations is 5 divided by 2 times n times log n. If we again ignore the constant factors, then we end up with n times log of n. Thus, the performance of merge sort is O of n times log n operations. Let's compare n times n, which is selection sort time, with n times log n, which is the merge sort time, to see the difference in growth rate. As we can see, by the time we get to 32 elements, the n times n algorithm takes 5 times longer than the n log n algorithm. The actual difference was smaller due to constants and constant factors, but we can still expect selection sort times to grow at a faster rate than merge sort times. Thus, when we need to sort many elements, we should choose merge sort.